Okay, so you should be able to see my window, and then we'll make it full screen. Can someone confirm that you can see my window?
Yes, sir, we can
Yes,
see.
sir.
Okay, wonderful. So we started looking at functions, right? We just had a very brief intro into functions. We didn't have much time, so I'll just start anyway, covering from functions today. So we are programming in a functional programming language, and as the name would suggest, the functions sort of play a big role in OCaml. Okay, so one thing I want to say about this lecture is you're going to see a lot of new concepts, right? Sometimes you'll feel that why are there so many concepts? This is so overwhelming. And what you'll end up seeing after we cover a little bit of OCaml is that we will sort of get to the essence of functional programming languages using this very small language called Lambda Calculus. It's a 3 instruction set language, right? So we saw one instruction set language in our intro. There'll be just 3 instructions, but you can sort of study the entire complexity of what we are doing here just through those 3 constructs. Okay, so my take on this lecture is you'll keep seeing a lot of things, right? So don't get flustered. I just keep sort of taking them as they come along, and then we'll sort of you'll get used to it after some point, and you'll start seeing the same pattern being applied in, say, JavaScript or C# or other languages, and you'll just feel familiar at that point. Okay, functions. So OCaml allows you to define anonymous functions. These are functions which don't have name, which you can sort of describe on the fly. So anonymous functions have the syntax where fun is a keyword. They take a number of arguments, x1 to xn, and then an expression, right? When you define an anonymous function, it's just a value, right? There is no further computation to do. E can be any expression, and just like you would define functions in other languages, E is not evaluated until you apply this function, right? You pass the arguments to this function, and then evaluation of E happens. So here is an anonymous function. So this function takes some x, right, and does x plus dot 1 dot. I think as we saw earlier, 1 dot is equivalent to 1.0. And that's a floating point value. So because 1.0 is a floating point value, and plus dot is a function for adding floating point numbers, x is inferred. OCaml infers the type of x to be floating point, right? If this is floating point, then it must be the case that this is also a floating point, right? Because those are the same variable. So what you get from OCaml is OCaml says, okay, you wrote this syntax for this function, and what I can see is that this function will take a floating point number, right? Takes a floating point number, and arrow is the function arrow. It sort of says what you're defining as a function, and the argument is a floating point number, and the return value is a floating point number. And we can't print the function definition because the function could be constructed on the fly, so it just says fun, where it says the static semantics is this type, and it's just a value, so it just is a placeholder there. Okay, so yeah, so this, if you run this, you'll get this. You can also change the type, change the expressions, and what you'll get is a different type now, right? So plus is an integer addition, and 1 is an integer. So x is being inferred as an integer, so this must be an integer. And if you mix it up, it's going to complain, right? So this is what we had seen earlier. So if you do this, because plus operates on 2 integers, 1.2 is a floating point number. The expression has type float, right? This expression has type float, but an expression was expected of type int, right? So, okay. Yeah, you're asking a very good question. I will defer that question for later. Really good question. So there's a question on chat, which I'm sort of looking at. What is the type of this function fun x arrow x? I will defer that question. There is something magical going on. It's actually very simple, but I don't want to sort of, you have to sort of, even though it's simple, you have to place it in a context so that it sort of, you can see the beauty of what is happening. So we'll come back to it later. So I know this is a question. I have slides on this question, so I'll definitely come back to it. Okay, so this is what I wanted to say. Anyway, I've said it. So here is another function, right? This is a function that takes a unit value, right? So recall that when we write this particular form, right? Open bracket, close bracket. It's sort of a value, a special value in OCaml. That's a unit value. The value has type unit, right? It's sort of like if you think about integers as a set, right, which contains all the integers. Unit is a set that is a singleton set that has only one element, and that one element is this value, unit value. So what we are defining here is a small function which takes a unit value. So we just write unit value here because that's the only possibility here, right? And it returns an integer, right? But the speciality of this function is there is only one value you can apply to it, right? So you can only pass it a unit value. So what's the point of this whole function? The point of this function is to suspend evaluation of the right-hand side, right? The right-hand side expression happens to be a value here, but if I do it as 1 plus 1, it won't evaluate until you apply the unit to it. I mean, this seems strange. Why would you want to do this? Imagine doing something like sending a message that is already known over the network, right? You just want to define a function that sort of says when you call this function, you just send a pre-canned message over the network. When you want to describe such a thing, you would use a thunk. A thunk is just a name for a function that takes a unit value and then returns anything. It just suspends the computation for the moment so that you can evaluate it later, right? So that's thunk. Yeah, again, I said, yeah, can we assign anonymous functions to? Yes, you can. So we will see that Ravi Gupta is asking a question. So yes, you can. We will come back to it. Yeah, so these sort of forms are there is a separation of ideas, right? So let me go through, and then you'll see what I want to say. Okay, so the cool thing with anonymous functions is they can refer to variables that is outside of their body. So imagine in C, right? So in C, if you want to actually, C doesn't have a good analogy. So let's drop analogies because C does not fit this well. So here is a definition, right? I define some let foo, right? Inside the body, sorry, inside the definition of let, I have let y equals 10 and x equals 5, right? And I define an anonymous function which takes a z and then returns you x plus y plus z. The key point I want you to take away is x and y are not arguments, right? They are actually referring to something that is in the environment, right? That is lexically scope. So in your scope, there are two variables called x and y, and you are referring to those variables, right? So, and the type of this function is going to be int arrow int because this is a function that takes a single integer, and these two have been referred to from the environment, right? So, and then what you're going to return is an integer. Essentially, the idea here is this is a function which takes some integer, right? And then adds 15 plus that integer and return that value, right? So you can sort of refer to things that are in your scope happily, and OCaml will not complain. Actually, it is very commonly used. So, yeah, okay. So the anonymous function here, which is the function that we defined here, fun z arrow x plus y plus z, is set to close over these free variables. So there are two concepts here, right? Free variables are those variables that are not bound by the function arguments. So this z is not a free variable because it is referred. It is being passed as a function argument, right? But x and y are not function arguments. They are being referred to elsewhere, right? And these are known as free variables. And this function is set to close over those free variables. This is just terms, right? there is no syntax over it, but we just tend to use these terms. So that's why I highlighted it here. So this anonymous function, you can just look at this anonymous function and you can see that x and y are not being passed as arguments. So we say that x and y are free variables, right? And this function is closing over these free variables, right? Just take those things as terms. We'll use them repeatedly when we come to studying more deeper concepts, lambda calculus. Okay, what I should do now is actually clear uh, all of my output. Otherwise, I'm giving away a lot of things that I want to say. Okay. So anyway, I've given it away. But anyway, so what is the value of res? So here I'm defining bar, right? Where I say let x equals 5 and fun y. I'm defining an anonymous function which refers to um, x here, right? Which is 5. And then I do, I just add the result. So the result is going to be 15, right? Why? Because bar is going to be this anonymous function, right? Which takes an integer and then returns an integer. And x is bound to 5. When you pass y is 10, you get 10 plus 5, which is 15. So that's the result. And in particular, I want you to notice that to answer Ravi Gupta's question, right? So you can bind this to, so we are binding this anonymous function to a variable here. So bar gets the function, right? This function, and this function type is going to be intervent. So you can sort of let bound these anonymous functions by that's how you give it a name. And this is function application. We just pass the value of 10 to bar, and then we apply the function to get 15. Okay, so a couple of concepts here. I'll keep moving. So yeah, so the distinction that I wanted to make here is when we studied let definitions, right? We said we can use let to bind the result of any expression, right? And I also mentioned functions are also values, which by definition means they're also expressions. So what is happening here has nothing to do with anything special to functions, right? Functions are just values. So just like let definition can sort of name any value, we are just naming a function value. So these concepts are quite separated, right? So you can sort of see that functions are one thing, this let definition is another thing, and we are just combining those concepts to give names to functions. So this is unlike what we've possibly done in C and Java and other languages, right? Where function definition, we sort of associate that with the name. So here we sort of have more fundamental operators. So you have let definitions and then you have anonymous function, and we just name those things together. Okay, and the beautiful thing about functional languages is functions are values. So you can pass values around in any language, right? You can send values, return values, and similarly in functional languages, you can have functions that takes functions as arguments and even return function as arguments, right? So this is a very powerful language feature. You might have come across similar concepts if you have studied function pointers in C, right? But as we will see, the functions as values concepts goes much further than in C. I'll just leave it at that. So just sort of, if you want to sort of frame this idea in your mind, right? How do I imagine functions taking arguments and function returning functions as functions? It should be functions, not functions as arguments. Function can return functions. Think about function pointers, right? You can imagine a C function taking a function pointer and also returning a function pointer. But obviously the concept is much more powerful here. And we'll sort of slowly see all of that. So I showed you a very small example of how to apply a function, right? Apply a function is also like calling a function. but we tend to use the term apply in functional languages because it sort of fits within the ethos of what we're doing here. We've already seen one example, right, where we've applied bar to 10, right? We say function bar is being applied to 10, and the general form is this is the syntax. So you have some expression E0, and then a series of expressions from E1 to En, right? And there is no parenthesis necessary. So you don't need to use parenthesis. And the way to read this is you are applying function E0 to N arguments. Okay. So here I'm using a very general form, right? I'm using expressions here, and all of these are expressions. So obviously there has to be evaluation of each of the expressions before we can apply this function. And what happens during evaluation? You can sort of think about this as the dynamic semantics, right? Recall the first class where we said every form has a static semantics and a dynamic semantics. Static semantics is the type. Dynamic semantics is what happens when you actually evaluate the expression. What we are seeing here is the dynamic semantics of function application. This is very intuitive, right? This is what you think should happen, but I'm sort of placing a name around that concept. So what is happening here? So we have these application form, right? So you would go ahead and evaluate each of these expressions in one order, right? So you would go from left to right order, and then each of these will reduce to a value. So evaluate E0 to En to V0 to Vn. As I said, functions are just values. So type checking will ensure that V0, which is a value, is a function whose type is this, right? It's sorry, not the type. The form is this, where it takes n arguments and then returns some expression, right? Type checking will ensure that. And what we do is we take each of these V1 to Vn, substitute for each of these variables x1 to xn. When you do substitution, you simply get another expression, right? So you take this expression wherever x and y and z and other variables are there, you substitute the actual arguments, you get another expression. You go ahead and reduce that expression to a value v, which is the result, right? So this is how evaluation is actually seen. In imperative programming, we tend to associate calling a function and returning a value, right? We still sort of interchangeably use those terms, but really what is happening when you think about function evaluation is what I've described here. You take a couple of expressions, right, E0 to En, you reduce each of the expressions to V0 to Vn. V0 is ensured to be a function type, right, whose form is x1 to xn gives you E. You take each of these V1 to Vn, substitute for wherever the variables are, right? So all of the variables are applied, and all you get is this expression. This expression will be a complicated expression now, right? And then you go ahead and reduce the expression according to the expression semantics, right? And you get a value v, which is the result. So this is what actually happens when you do function application, right? So there is no we don't tend to associate calling a function and returning a value. It's sort of reduction, right? Everything is sort of taking an expression and then seeing how can we reduce this expression further. That said, you can use these terms interchangeably. I'm not going to be very stringent on you have to use these particular terms, but that's just to give you a comparison of what happens between functional languages and imperative languages. Okay, so here are some examples. So I have a very simple function which takes an x and then returns you x plus 1. So I take this anonymous function, right? That's a value, and I apply 1 to it. So what happens here? You would expect the natural thing, right? So the way you have to imagine this evaluation is you evaluate this to a value. So we know function, anonymous function is a value. 1 is also a value, right? 1 is a value. So now you substitute in this body expression, wherever you find x, substitute 1. So you get 1 plus 1 expression, and then you reduce it, you get 2. right? So that's what is happening here. And in the same way, you can have multiple arguments, right? So you can have x, y, z, and then x plus y plus z. And this is going to do 1 plus 2 plus 3, right? So that is 6. So one thing that I should stress here is there are no multi-argument functions in OCaml. So I've used multiple arguments here, right? It looks like I am this function takes 3 arguments x, y, z, and then returns you x plus y plus z. This is actually a syntactic sugar. Syntactic sugar is like some helpful syntax for this other form, right? The form is this. Because I said the function can take values and return values, the way you have to read it is this function, right, expects one argument, right? It expects an x. When you apply this function to one argument, it is going to return a second function, right? It's going to return this function, which takes one argument again, right, which is y, and it's going to return another function, right, which is this function. And the last function, the third function, is taking one argument, right? And then it is going to perform x plus y plus z, right? So this is really what is happening when you write the form where you take 3 arguments. It is actually expanded to by the compiler into something like this, right? So the way to read it is fun x is a function which takes one argument and then returns a function, this function, which takes again one argument, right? Which again takes one argument and then performs this computation. You can use this interchangeably, but you sort of see that there are no multi-argument functions in OCaml. It's just syntactic sugar. The semantics is the same as, exactly the same as this form, right? And as you would expect, this gives you the same result. But the key takeaway is this, right? So in many languages, you sort of see functions taking many arguments as like a primitive, right? When we say primitive, it is embedded into the language. Here, even though we have special syntax for it, it is not at all special. The semantics, the static and dynamic semantics of this particular expression, it is the same as the static and dynamic semantics of this expression, right? So these two expressions are equivalent in terms of the static and dynamic semantics. Okay, so right, so multi-argument functions do not exist in OCaml. I mean, at this point, you might ask, okay, this might be inefficient, right? But actually, the compiler is very smart. So it optimizes it to a form where it has the same cost as what you would expect in a multi-argument function. But that's beside the point, right? So we don't care what the compiler does in this course. You are studying compiler's course for that. So I will leave all of that there. All I want you to take away is that these sort of forms are just special forms, right? When you think about functions that take multiple arguments, in your mind, sort of imagine that you can also have functions that take one argument, return another function. Okay. So that's that. Yeah, so just to make it very concrete, we can use let to name functions. So here is one useful name for this function, right? The function is take an x and then return x plus 1. I can give the function the name suck, which means successor. So successor is a function that takes one argument and returns the successor value. And again, this is semantically equivalent to writing it this way, because writing it takes more characters, more keystrokes, right? OCaml sort of allows you to do something like this, where you say let suck x. You sort of now read this suck as a function. Sorry, you sort of read suck as a function definition, which takes one argument and then gives you x plus 1, right? So just to we do like all of these syntactic sugars, right? Because they save a lot of time. So we will see this form, which is let suck x equals x plus 1, a lot more often than this form. you're not wrong when you write this, but we will just stick to writing it this way. But again, my point is, when you see let suck x equals x plus 1, in your mind, think about the equivalence to a definition like this. You could have equivalently written the same way. Okay, so Anirudh A has a question. So I do let my func equals fun x fun y. Yeah. So Anirudh has a question. Yes. So here's the question. I'm just looking at the chat, but I'll try to run it here. Yeah. So this has to be a let, right? So we can't use val. This will be a let and then in. So yes. So we are defining a name, right? And then we define this function, which takes one argument, right? So you take one argument and then you return a function, right? Which will expect one more argument. And if you run this, you'll get 15 because then you go ahead and apply the body, right? So because every multi-argument function is a function that takes one argument and returns a function, you can just supply one of the arguments. Okay. Yeah, I'll delete this one. Then continue. What if we have x minus y? Yeah, that's fine. So you'll get minus 5. I think I can go back to. So these are integers, right? They go from negative, positive int max to int min to int max. So you can do. Let me try to undelete the cell. Undo delete cell. I mean the order of arguments. I don't get the question. So can you speak perhaps? Sarthak Kapoor, you want to unmute and say what your question is? I don't think you mean this, right? You don't mean this. Okay, so let me move on. I think you'll see. So you want to do something like this. Okay, so you want to do y x. This will be 5, right? So you just naturally progress and just do substitutions, right? So if you reorder the arguments this way, I mean, there's nothing magical going on. So this is just yeah, so my point is these are very simple, right? So you just go to this particular slide and then keep doing the same thing, the recipe that is prescribed here, will get to the values. There is no magic.
Sir?
Yeah.
Sir, I think the doubt is when we write functions in this way and we have multiple values like 1, 2, and 3 we wrote, then which value will be assigned to x, y, and z? That was
Oh, no. So these are good questions. So these are so x is not special, right? So we are not assigning to x. So these are positional, right? Just like you would. I think is that am I sort of making sense? So when you apply a value, you're not applying to. You are only applying to the first argument. You are not applying somewhere deep inside for x. Is that the question, Naman?
Sir.
Yeah.
Yeah. So actually, above you have written a conversion of fun of x, y, z equals x plus y plus z 1, 2, 3, right?
Yeah.
Shouldn't it be in the reverse order then, like z, y, x maybe? I'm not sure though.
No need. Why would? So you wanted?
No. Like up. Can you just go up for a minute?
Yeah.
Like here, which variable is assigned to which? Like which gets 1, which gets 2, which gets 3?
So x gets 1.
Okay.
Y gets 2.
Okay, fine.
And z gets 3.
Okay.
See the reading is this, right? So
Yeah.
So I think it's a question of where the brackets go. Is it? So if you sort of imagine it this way, right, then it becomes clear, right? So this is a function that takes one argument. You can sort of ignore this for the moment. You can just ignore it for a moment. It does something with x. right? So x happens to be assigned internally here. So that shouldn't really matter. There's only one simple form. Yeah.
So,
Satak? Yeah.
am I audible, sir?
Yeah, you are.
Actually, like we had that doubt whether it's evaluated bottom up or from top down. Like, I mean, how does the compiler assign values to the variables?
So there is only one form, right? So which example do I take? So let me just take this example, right? So make it slightly bigger. So what is
Is it
happening?
correct to, so is it correct to say that the first variable that is mentioned in the function definition gets assigned the first argument and so on?
Yeah. So it's what you would expect in a natural in C or something, right? So you would just if you pass one argument, it gets assigned to the first one. If it is second, then it gets to the second one, right? So here this one goes to x here, right? See, we'll just reduce it by hand, right? So what happens here? Are you clear with this example, or should I reduce it there? So here I take 1, 2, 3, right? So it could be 1, 2, 3. So 1, 2, 3. You just replace wherever you find x, you just replace that with 1. And similarly, 2, you just replace that with 2 here. And same for z. So you get 1 plus 2 plus 3, which is 6. And here you can sort of do this reduction by hand, right? So let me just write it this way. So this is equivalent to doing one step of reduction. You are going to substitute you just look at this one, right? Okay. I can see what the issue is. If I make all the brackets explicit, maybe it's clearer. Yeah. Yeah. This is the way to interpret it. So the first thing it looks at is, oh, there is a function definition here, and you are going to apply it to one argument, right? So I've applied 1 here. So 1 is applied to x. So now substitute wherever x is there with 1. So now what you will get is, you'll get this body, right, where x is 1, and then you have 2, 3. Now the question is what happens next. Then it says it interprets this way, right? So now you look at 2, you substitute 2 for wherever y is, and this expression now reduces, right? So you get this expression, and then y is substituted, and finally you have 3. So 1 plus 2 plus 3. So function application is left associative, right? So when you look at f of a, b, c, you see it as f of a applied to b, right? Applied to c. I think this should answer some of the questions. Sarthak, does that answer your question? I think you started the question initially. Okay, so I think I should probably mention it in the next time I teach this course. So yeah, function application is left associative. So when you see FABC, right, you sort of read it as F applied to A, and then that is expected to return a function, because otherwise the program wouldn't type check. So then this is interpreted this way, and finally this way. Thanks for asking like beautiful questions, right? So these are very, very useful questions for me. Okay. Any further questions on this one before I might have confused more people by explaining it badly. So I just want to give you an opportunity for just, okay. So one more question. You have fun xy, arrow x plus y. Yeah, you need to give brackets properly. So I think, yeah. So we can try this, right? So, okay, we have this. So what is how is it going to interpret this one, right? So it's going to be very confused by this. It says syntax error because you sort of have to provide brackets for values when you encapsulate function, anonymous function. It is always nice to give brackets, right? Otherwise, the parser would be very confused. You will study lexers and parsers in OCaml, in the compiler's course, and you will see that this is quite tricky to parse. Okay, so now you have a nice thing, right? This is no longer a parser error. You have this valid form here. You have a valid form here. One valid form somewhere, valid form somewhere. What do you think will happen now, right? If you sort of interpret what I said before, right? Just look at this one. If you have expression E1, E2, E3, E4, E5, you reduce all the expressions first. So I reduce each of these anonymous functions are reduced values, right? So this is a value, 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 right? Okay, so 2 people say 4. Does anyone want to say something else? let's just go ahead, right? So apply this left associativity rule now, right? So you look at expression E0, E1, E2, E3, E4, which is now V0, V1, V2, V3, V4. Yeah, so Ravi Gupta has caught it. So it's an error, right? Because first thing it's going to do is it's going to look at this and say, oh, I'm going to reduce this expression. Okay, so the type inference, yeah, so you can't, yeah, that's the answer. So you can't add a function and integer, right? The type inference is going to infer the type for this function as from looking at plus, right? It knows that this is a int function. So it takes 2 integers and then returns an integer. So it expects the arguments to be an integer, right? This is not an integer. This thing is a function. It's a value, it's a function. So you're going to get an error, right? So yeah. What if you added parentheses? Yeah, you can. Yeah, that will solve it. So the question is, what if I added parentheses? You need one more parenthesis. So the idea is that parser again will not know how to parse the second argument. So anonymous functions have to be parenthesized properly. So if you parenthesize this way, it'll be fine, because again, go back to that rule, right? Each expression, reduce it to a value. This is a value. This is not a value, right? This is a function application. So you can reduce it, and this reduces to 2. Again, this is a expression function application that reduces to 2, and then you finally apply it. So this will reduce to 4. Okay. Any further questions? Good questions. These are really good questions. Okay, so I think that might have solved some of the confusions. So we'll continue with what we were seeing earlier, right? How adding parentheses solve the error. So okay, so let me try to do this again. So oops. So when I look at this one, right, there is a question in the chat which says, I don't understand how this solved the error. When I look at it this way, it looks like 5 expressions, right? 1 expression, 2 expression, 3 expression, 4 expression, 5 expressions. All of these expressions are values. So when you sort of have all of these as values, and you have this form where you have V0, V1, V2, V3, V4, OCaml is going to say, I am assuming V0 is a function, right? I'm going to now apply V1 to it. So it is going to do this reduction first, right? It's going to do sort of do this first. Okay, so just look at this particular form. This is wrong, right? This is wrong because this is a function. This goes and gets substituted here. and this becomes something like this. Yeah, something like this. You can't add a function to a any integer. That wouldn't type check. So the type checker will complain. Okay, so it's going to break in some way. So that is not good. Why does the adding parenthesis solve it? When you add a parenthesis here, there are only 3 expressions now, right? There is E0 here, E1 here, and E2 here. So OCaml is going to look at it and say whether each of these expressions are values. The first one is a value. That's just the anonymous function definition. So that's a value, right? Is the second one a value? It's not a value, right? It's an anonymous function applied to 1, right? So E1 can be reduced. So E0 will just be the same thing. E1 is apply 1 here, right? 1 where x is. So 1 plus 1. This becomes 2. And the same thing for E2, where this is a function application that can be further reduced. So this becomes 2 as well. Now keep doing the same thing, right? Now you have E0, E1, E2. E2. Are these values? Yes. So 2 and 2 are values, and function anonymous function definition is a value. So you have V0, V1, V2. Now you go ahead and apply, right? So x gets the first value and y gets the second value. So you have 2 plus 2. Yeah, 2 plus 2, which is 4. So that's why the error is solved. Okay, good. Okay, that's good. So any further questions? It's important you understand how functions work because you'll be using functions left and right all the time. So the thing that I didn't mention but to take away is that function application is left associative. Okay, so you sort of read the brackets from the left, and that should clarify what's going on here. Okay, now function definitions. Yeah, so too big, so let me reduce it. Okay, so you have a successor function which is x plus 1, and of course you can define the function. Now you get the name, right? So the type checker says, oh, you're defining a function which is a suck, and it takes an integer, returns an integer. Suck 10 gives you 11. Okay. Yeah, this is just repeating what I had said earlier, right? So you can have functions that take 2 arguments, right? I'm defining an add function that takes x and y and does x plus y. You sort of read it as add is just a name for an anonymous function, right? That takes 1 argument, returns another function, right? That takes 1 argument and does x plus y. I mean, this sort of reading is not always useful, but the point is they are equivalent. So oftentimes we'll just say add is a function that takes 2 arguments, right? And these are equivalent. So yeah, and this should give you addition's result, which is 15. And maybe I've mentioned it earlier. So the thing that is happening here is I have a definition of add here, which is a top level definition, right? I have another definition of add here, which is also using the same name, right? So when I call add here, I'm referring to the closest one in scope. So the closest one is the last defined one, which is add here. So what is happening implicitly is this add is shadowing the previous definition, right? So it could be just for fun, right? So I can do it like this as well. I can mix it up as I want. I think this should work. Yeah. What I did here is I defined 1 argument here and 2 other arguments are taken here, right? So if I just give say 20, It'll give me 35, right? Now this add is actually taking 3 arguments here. That's the add that I'm referring to. And this definition of add has been shadowed with this definition. Okay. So yeah, so because of this view, right, where we said every multi-argument function is actually a function that takes one argument and returns a function. You don't have to pass all of the arguments to a function, a multi-argument function. So here is a function which takes 3 arguments and then returns x plus y plus z. If you just apply it to 1, it is going to return a function. I think we've seen this working through that example, right? So you'll get, you'll substitute wherever x is 1. So this becomes 1. And what you get in return is you have a function that takes 2 arguments, right? Y and z, and then this expression. And you can give name for this, right? These are just values at that point. This is just a value, right? This is fully evaluated. This is just a value, so you can name it. So I have a name called foo, which I give to a function that takes that to this form, right? So there is an anonymous function that adds the 3 arguments, but I just supply one of the arguments to this. So when I just supply 1, you get this back, right? So foo is a function that takes 2 arguments, right? Adds them up and then adds 1 to it, adds 1 to the result. So here it is going to add 2 plus 3, right? Because it is going to add y plus z. And then this 1 is already substituted. So it is also going to add 1. So you get 6 in return. Right? You can mix these syntaxes up. At the end of the day, everything is just a single argument function that may return another function.
Sir?
Yeah.
Sir, I wanted to ask, what is the type of foo?
Oh, type of foo is int arrow int. Good question. So while function applications are left associative, right? So let me try to phrase it properly so that again I don't say something wrong. So when you have FAB, right, we sort of read it as f of A applied to B, right? So, but when you write enter end, the typical reading is it takes 2 integers and returns an integer, right? But that's not the only reading, because everything is like a multi-argument function is just a single argument function. The bracket actually is right associative here. This might be confusing, but just go with it. So the way you have to read it is this way. Okay. So the type of foo is a function that takes 1 argument, right, and returns a function that takes 1 argument, right, and returns an integer.
Sir?
Yeah.
Sir, so there is no explicit type called fun. So everything is written in this form, int gives int or whatever the form of is.
Yeah, arrow is the function format, right? So when you write arrow here, that really means function.
Okay, sir. Okay. Yes,
yeah,
sir.
and then you can also partially. So why is this reading useful, right? I read the type int arrow, int as for types, the brackets go right associative, right? So this is a function that takes 1 argument and returns a function that takes returns a function that takes 1 argument and returns an integer. Why is this reading useful? You can partially apply any multi-argument function. Foo is a multi-argument function, right? So you can partially apply it. So you get int arrow int function, right? And again, you can name this thing. I can name it as bar, right? So bar is int arrow int, and then I can apply bar to 3, which gives me 6. So you sort of, yeah. Venkat?
Yes, sir, understood. So
Yeah, okay.
function has its own like unique typecasting, the way it's typed.
Yeah, so
Depends
there's no typecasting. You sort of say it has a type, right? You just define the function. OCaml infers a single type for it.
Okay, sir. Yes.
Okay, and yeah, so the fact that we don't explicitly do multi-argument function is helpful because we can partially apply any function that expects more than one argument. I think I'm out of time. So yeah, so I'll just stop here and then we will continue in the next class. These are really good questions. I think the class is very interactive, even though we are in this weird situation. But we'll continue tomorrow. Thank you.